All right, welcome back to our last week of lessons here for Chem 30 in the equilibrium unit. So this one right here, we're going to be focusing on acid and base strength, and more importantly, the equilibrium law, how it incorporates or how it works with weak acids. Now, just a little reminder, we covered this last week. When we have a strong acid, the concentration of hydronium is equal to the concentration of the strong acid. It is not in equilibrium. So to calculate the pH, we can just take the negative log, the concentration of a strong acid. In this case right here, we have nitric acid. Its concentration was 0.5. So that means concentration of H3O plus is equal to the concentration of HNO3. So we go negative log of 0.500, and we get a pH of, sorry, just let me plug this in here. .301. So, of course, last week there was a bunch of different examples we'd done where we looked at strong acids and strong bases, only specifically those. We did not delve into the weak ones. So now for this lesson, we're going to look at how to calculate equilibrium stuff, how to calculate pH and pOH for weak acids, and tomorrow we're going to look at weak bases. So remember, for a weak acid, they only partially ionize in water to produce the hydronium ions, and for the most part, they're less than 50%. So that means that the ionization constant for the acid, or the equilibrium constant for the acid, is generally less than 1, or the reactants are favored. So we cannot say that the concentration of hydronium is equal to that of the concentration of the acid. We will need to use equilibrium. So there's two different ways that we can actually calculate or communicate equilibrium positions. One of those is percent ionization. So percent ionization, we have our formula right here. So we take the concentration of hydronium and we divide that by the concentration of our original acid and multiply by 100%. So of course, we need to figure out how to calculate concentration of hydronium. So we can get this in two ways. So from a pH or ice tables. And that is using the ionization constant for an acid, or the equilibrium constant for an acid. So we're going to look at two of those for today, and then of course applying it into this equation. Now we are going to work with a little bit of this equation. First off, just with a few examples here on how to calculate percent ionization. Now in these here, the concentration of hydronium and the concentration of the acid are given, so it's more or less just plugging stuff into the equation, right? So when we look at example 1, it says calculate the percent ionization of a 0.5 moles per liter solution of hydrosulfuric acid. Remember, that is H2S. That is a weak acid. If the concentration of hydronium is 5.0 times 10 to the power of -4. So our formula, percent, is equal to concentration of hydronium over concentration of our acid times 100%. So our hydronium is 5.0 times 10 to the power -4, not 14, 4, over concentration of our acid was 0.500, and multiply this by 100%. And in our first example, we get a 0.10% ionization. All right, so if we had to write this inside of an equilibrium law, that 0.10% will go up on top, and of course we get HS minus plus H3O plus. Now I know this question doesn't stay right at an equilibrium law, but that's how we can take this percentage and put it inside of our equilibrium. And we've done this previous examples as well when we first did equilibrium back at the beginning of this unit. Now, example 2 is more of a typical question that you can see because the concentration of hydronium is hidden within the pH. All right, so our first step is, of course, we need to find concentration of hydronium, and we have the concentration, we have pH, and of course we have the concentration of our acid. So, first step, concentration of hydronium is 10 to the negative pH. So you should have had a lot of practice that there last week. So we got 10 to the negative 2.38, and we get a concentration of hydronium of being 4.168 0.87 times 10 to the power of negative 3 moles per liter. So from here, now we have enough information because we have a 0.1 mole per liter solution of methanoic acid. So we go percent ionization is equal to the hydronium ion concentration over our acid times 100%. So the hydronium we just calculated from the pH. Our acid is given in the question, 0.10. And we get a percent is equal to, in this case right here, 4.2%. Sorry, I kind of ran out of space there. But we get our percent of 4.2%. Now this question to write the ionization equation for this acid, including the percent ionization. So we know it is 4.2. Sorry, this was a drawing of filtration I had right here from Chem 20. So if we wanted to write out that, our methanoic acid, of course, the chemical formula for that, you can check your data book, it's HCOOH plus, it's a methanoic acid solution. So that means it's just reacting with water at 4.2%, and we get HCOO minus plus H3O plus. And that is taking that last little bit, writing it the equation. Now for the next two examples, it's taking the equation and rearranging it and solving for something else. So when we look at what would be the concentration of hydronium if a solution is 2.55 moles per liter of acetic acid and the percent ionization is 0.866%. And of course, example 4, what was the concentration of the unknown acid if it has a 5.89% ionization and a concentration of hydronium of 1.41 times 10 to the power negative 2 moles per liter. So of course, with these two questions right here, you're rearranging the equation of this and solving for your unknown. So in example 3, you're isolating for hydronium, and example 4, you're isolating for the acid. So I'd like you to pause the video and see if you can rearrange and solve those. So do that now because the answers are going up in 3 seconds. Okay, so for 3, we get concentration of H3O plus should be 0.0221 moles per liter. In example 4, the concentration of our unknown acid, or the concentration of the original acid, should be 0.239 moles per liter. So if you didn't get those, just kind of let me know, because we can probably go through and set up a Google Meet and just kind of rearrange these here, but I don't want to spend too much time on it because it's just algebra. It's rearranging that one formula and solving for one of the unknowns. Now, for our method 2, so this is where we are going to calculate the hydronium ion concentration using the ionization constant for the acid or the equilibrium constant for the acid. So where we get these right here, we can use from our table of acid and base strength because we have this value right here, Ka. So remember, K just stands for equilibrium. So this little subscript here, A, just stands for the acid. Now, for this chapter, we kind of refer to this as the ionization constant, but really what it is the equilibrium constant. So if I say ionization constant for the acid, it is the exact same thing as saying equilibrium constant for the acid. Or if I say the words equilibrium constant for the acid, I'm still talking about the ionization constant. So two of these terms are going to be used interchangeably. So I'm just going to switch back and forth between using them just so you hear them both. So what we have right here, the acid ionization constant or the acid equilibrium constant can be used to communicate the strength of an acid, the position of equilibrium, and also to calculate the hydronium ion concentration and, of course, the pH of solutions. Now this is just like when we done using the equilibrium constant to solve for equilibrium concentrations. So we've actually done this work before. Now we're just applying it to an acid and base system where the equilibrium constants are actually provided to us. So the value for the ionization constant or the equilibrium constant is directly proportional to the concentration of hydronium, because this is still an equilibrium constant. So as we know, the bigger the equilibrium constant, the closer it is to 1, or even if it's above 1, the higher the value, the more the reaction favors the formation of the products. And remember, for like the reactions we just done, one of the products is always going to be hydronium in these equilibrium systems. So of course, if we can figure out the concentration of one of the products, we can figure out pH and all the other stuff. So the larger the value for the equilibrium or the ionization, the stronger the acid, and of course, lower the pH. So all of these values can be found in our data booklet, and we will need to use equilibrium laws to evaluate pH, hydronium, and hydroxide for weak acids and bases, and we might have to use base tables. Now, generally, what we get, the equilibrium expression for weak acids, we have our acid. Water is going to act as a base because it's going to take that hydrogen. We form our conjugate acid and, of course, our conjugate base. So the equilibrium law, we notice we have hydronium and this anion in our products. So we write out our products over our reactants. Now remember, water is a liquid, and in all equilibrium expressions, we omit pure liquids. So that means we leave out H2O and we just have the concentration of our acid. And that is it. So omit H2O because it is a liquid. Now, so in order to calculate Ka, so we're either going to use Ka from our data booklet or we're going to calculate it. Just depends on what the question's asking. So we're going to start with actually evaluating Ka given a pH. So for example, our first right here, the pH of a 1 mole per liter solution of acetic acid is measured to be 2.38 at SATP conditions. What is the ionization constant for acetic acid under these particular conditions? So our first step for this right here is always going to be write out our equilibrium or our ionization expression, because we need to see the reactants and the products. So in this case right here, we have acetic acid, so that's CH3COOH, plus it is a solution, so the only thing that's present in there is water. So this acts as the acid, this acts as the base. We get the acetate ion in return. And of course, we also get hydronium being produced. This is the conjugate base and conjugate acid, keeping those terms in mind. So that's always going to be the first step. Write out the reaction. And of course, with chemistry, that's the first step in almost everything we do is write out the reaction. Now, generally, our second step as well, it's handy to write the equilibrium law just to kind of see what we need. So as mentioned before, we leave out water because it's a pure liquid. So in this case right here, our equilibrium law is products over reactants. Oops. So we get our acetate, we get our hydronium all over our acetic acid. And what we can do from here as well, because we are given the pH of a solution, we can find the concentration of hydronium. So this is just kind of how we start off with all our questions, and once we get past this, then we can start kind of filling everything in. So the pH was negative 2.38, and we're left with 4.2 times 10 to the negative 3. Now, you could keep more digits if you want. which will probably be a good idea. This isn't really the final answer, so I should probably keep a few more digits just in case. So let me just rewrite this into 1,687 times 10 to the negative 3 moles per liter. All right, now from here, we kind of have, we only have at this particular point in time this to go in here. Right now, one of the problems is that we do not have the other equilibrium concentrations. So for the acetate ion and of course the acetic acid. So that's why once we do this ice table, an ice table will be important. Now, once you get really good at these, you won't really need to do an ice table. They're just really handy to do. So originally, our acetic acid was 1 mole per liter. Water, we don't worry about it because it's a liquid. Our products were 0. Now the coefficient in front of acetic acid is 1, so it's going to go minus 1x, whereas our products is going to be plus 1x for both. 1.00 minus x for our acetic acid, and these are going to be x. Now, luckily, we have right here, we have our x value, but we also found this right here. So what you can do is, remember, if you have two values for equilibrium, you can write them both in. Because you can equate two of these to get something. Now, there is a little note here on the precision rule, and that is basically if you do have an extremely small number, let's say x is super small and we try to subtract it from 1, then it's not, the 1 is kind of unaffected. So for example, if you look at, we go 1.00 minus our 0.0042, so precision rule for significant digits is that you only go to, in this case right here, the lower number significant digits is 2 points after the decimal. When you look at this, 2 points after the decimal, you're basically left with 1. Now, the precision rule is handy to do. I like to ignore it though. If you actually look in your books for Chem 30, they kind of explain this as well, but honestly, don't worry about it. I say not follow the precision rule and actually do this. So we know x so we equate two of our things, and we can say from our ice table that x is equal to 4.1687 times 10 to the negative 3. Now from here, we know concentration of H3O plus is equal to 4.1687 times 10 to the negative 3. Concentration of our acetate, CH3COO minus, is equal to X, so that is also equal to 4.1687 times 10 to the negative 3. And concentration of acetic acid, CH3COOH, is equal to 1.00 minus X. Now, this is where the precision rule comes in. Like, X is significantly small enough where it really is not going to change the value, but there's going to be somewhere it does and somewhere it doesn't. So this is why I still like to do this step and kind of ignore the precision rule. I'm just kind of running out of space there. And we get 0.99583. So now we have at equilibrium the concentration of hydronium. At equilibrium we have concentration of the acetate, and at equilibrium we have concentration of acetic acid. So we plug this in to our equation. there's a lot of writing for this, so I'm going to shorthand this because hydronium and the acetate are the exact same. So I'm just going to shorthand this and square it because we're the exact same thing getting multiplied together. And we end up getting, once we do all this, 1.8 times 10 to the negative 5. And of course, that is with the correct number of significant digits because of the pH only had 2 significant digits. If you did the precision rule, you would still get the exact same answer with rounding. Now, if we kept more digits, obviously it wouldn't be the same. Now that's where, once again, you can follow the precision rule if you remember precision rule for adding and subtracting significant digits. If you don't remember, completely ignore this and go and do these steps just like that. So our example 2, this one kind of had step-by-step for you. So example 2 does not have these step-by-steps. It just says a 0.25 multiple liter solution of carbonic acid has a pH of 3.48. I almost said carbonaric acid. Carbonic acid is 3.48. Calculate the ionization constant. All right, so just like before, you want to write out the reaction. And of course, it is in equilibrium. And of course, we want to construct our ice table as well. So initially, we have 0.25 water. We cancel out. Our products are 0 and 0. Our carbonic acid minus X, our hydrogen carbonate ion plus X, our hydronium plus X. We get 0.25 minus X, X, and X. So from here, of course, we haven't used our pH yet, which we're going to do. Now, we don't really need to kind of do all the steps that we did last time because we can see here the hydrogen carbonate and hydronium are both X. So as soon as we find hydronium, we find the hydrogen carbonate. So concentration of hydronium is equal to X, and that is equal to 10 to the negative pH. So this is just kind of taking a few shortcuts here, right? Understanding that they're both the same. And when we do this, we get X is equal to 3.311 times 10 to the negative 4. So by solving for X, we just found this and this. And we can use that to then solve for this. Now, you can put in all this and like kind of I did what last time, write out all the values. Another thing that you can do, once again, just if you want to save time and space, is that if you know the ionization constant for the acid, I'm just going to do this off on the side right here. Didn't mean to go down that far. So if we did Ka is equal to, we know it's HCO3 minus H3O plus all over H2CO3. We can put in our equilibrium concentrations, and then we can actually solve. So put in all the values for X. Right, so I just combined X squared there, and of course, for some reason it's not writing here. Here we go. Oh, sorry, almost did that wrong. We have 0.25 minus 3.11 times 10 to negative 4. So I was just running out of space there, so I kind of shorthanded it a little bit. And we get K, oh, sorry, it's it's not 3.11, it's 3.31 times 10 to negative 4, and we get Ka, in this example right here, be 4.4 times 10 to the negative 7. So that is doing a little bit of a shorthand method. So that is putting all these values at equilibrium into our expression, right? So taking them, putting them over here, and then solving for x within the equation. Now with that, I want you guys to try this one. So pause the video and try this on your own. See if you can get the Ka for this one, kind of going through those steps as well. All right. So instead, pause it, do it the ice tables, everything like that, and see if you can get the answer, because the answer is going up in 3 seconds. And you should get the ionization constant is 0.014. Now for this one right here, if you want to see it worked out, just email me and we can actually go through Google Meet, or you can hop online, look at the answer key. So I have this one worked out on the PDF of the answer key there as well. But if you do follow the same steps we did up above, so writing out the equation, doing the ice table, finding hydronium, and then making those assumptions or those connections that the basically the conjugate base and the conjugate acid are going to have the exact same concentration, because this is always going to hold true, and so on, and filling everything in like that, you should do fine. Now if you have trouble, please let me know. Now the last one that we're just going to cover, and this is calculating hydronium using our ionization constant. So not all the time can you can actually get an accurate reading of pH of a solution. So sometimes you actually need to use kind of the data booklet in order to solve for pH, because it's not given. So, and that's why here, before the pH can be calculated, we need to get hydronium. So that's going to be true for everything, because we know pH is equal to negative log concentration of hydronium. So we need to get the concentration of hydronium in order to solve for pH. Now, if we only have the concentration of the acid that we start off and its ionization constant value, but not the concentration of any of the other ions, we can assume, that the concentration of hydronium and the concentration of the ion are always going to be the same. And the reason for that is, well, the ice table. And we've seen it up here, because no matter what, this was the A minus, and this, of course, is our hydronium. And this was our HA, and this is water. We don't need to worry about it. But because here we're always going to start initially with no concentration being formed, but as equilibrium established, you're always going to change with a 1-to-1 mole ratio between the two, because it's only a transfer of one hydrogen. So therefore, no matter what, the concentration of the anion and the hydronium ion will always be the same. So that means we can simplify our equilibrium law to this. And simplifying that, oops, not H0 plus, and simplifying it, if we rearrange, we get this formula right here. So our equilibrium expression can go, because it's going to be x times x up top, so basically x squared, and we know x is equal to concentration of hydronium. And that is also equal to concentration of A minus. So that's how we can get x squared up on the top, and the acid is going to be on the bottom. If we rearrange and solve, so we have to multiply both sides by this, and we'll get this expression right here. So now what we have is a way to actually calculate concentration of hydronium if we're given the ionization constant for our acid, and we are given our acid concentration as well. So we're going to look at actually applying this into more practical problems. Now, there is going to be a little bit of a problem though, in that this concentration right here, remember this is equilibrium. So there can be a little problem, and we'll see this right now. So let's just say we have a question like this, where we have pH of 0.250 moles per liter solution of acetic acid. So we have our equation written out like this. We can do our ice table, where we have 0.250, water we omit. This starts off as 0 and 0, minus x plus x plus x 0.250 minus x, x, and x. Now, if we did, so if we had that, now that's the only information we're given. So we can go and reference the Ka value for acetic acid using our data booklet. Right, so when you go to your data booklet, you find acetic acid, which is right here, and this is its ionization constant. So we write this in, have that, and then of course we can then fill out our equilibrium law. So we know in our top we're going to have hydronium squared all over HA, and filling this out, that means we get x squared over, in this case right here in the bottom, we got 0.250 minus x, and that is equal to 1.8 times 10 to negative 5. So you can tell right now this is basically setting up for the quadratic equation, right, where we have to simplify this and get it in the form of a squared plus b squared. Oh, so ax squared plus bx plus c is equal to 0. Now, I'm not going to go through all this, mostly because in Chem 30 you're not going to be expected to solve for the quadratic equation, but you definitely used the quadratic equation before in some of your previous ones, so you should be able to rearrange this expression right here and put it in this form. Now, if you did, I'm not going to go through all these steps just because of time, but either way, you would get your value for A to be 1, B would be 1.8 times 10 to negative 5, and your C value would be negative 4.5 times 10 to the negative 6. Now, if you want to see the workings for this, I do have it kind of up on the answer key in Google Classroom. But either way, like I said, you don't really need to worry about doing this because you're not expected to in Chem 30. I'm going to show you a second to avoid it now in about 5 minutes. So once you get your ax squared plus bx plus c, we plug our values into our quadratic equation where we have x is equal to negative b plus or minus root b squared minus 4ac all over 2a. That is a mouthful. But if you put the values in for a, here, b, in here, and here, and sorry, a also here. I'm not going to draw all those lines because it's just going to turn into a mess. Either way, you plug all those in, and the only x value that makes sense, you get x is equal to 0.002125. So, and as we know, that's also equal to the concentration of hydronium. So from there, you go pH, concentration of hydronium, that was the whole point of solving for that, and we get 2.68. Now, as we can tell, if you had to do the quadratic every single time, that's a lot of work. And like I said, you've done the quadratic enough in math class, that's why we're not going to be asking you guys to do the quadratic equation here. We're going to ask you to avoid the quadratic equation. And this is doing an assumption check. So what this assumption check is, we're saying that if the initial concentration of the acid is at least 1,000 times the Ka value, we can assume the initial and equilibrium amount concentrations are equal. So what that means is that if we take the concentration of our acid and we subtract x, we get the concentration of the acid. So let's actually look at applying this. So we just did it by using the quadratic equation, got 2.68 as the pH. So we're going to do the exact same question, except our first step is we're going to do our assumption check. So our assumption check is we take the concentration of our acid and we divide by the Ka. Now we're going to see if this is greater than 1,000. Now when we do this, we get 138,897, which of course is greater than 1,000. So that means the assumption check works. So what this means at equilibrium, the concentration of our acid minus X is equal to just the concentration of our acid. So when we write out our equilibrium expression, this stays the same. This is not minus X, right? So that means this is X squared, this is just 2.0. So we rearrange and solve. And we get concentration of hydronium we get 0.0021. And last but not least, just kind of ran out of space there, pH is equal to negative log concentration of hydronium 0.0021, and we get a pH of 2.68, which is the exact same answer. So by doing the assumption check, what we're doing is simplifying this thing right here. As at equilibrium, the concentration of the acid remains unchanged. So therefore, there is no minus X on the denominator, and therefore no quadratic equation. And that's why the assumption check is so important, is that all you need to do is do the assumption check. If it works out, you can then plug in this equation right here. Concentration of hydronium is equal to Ka, the square root of Ka times the concentration of the acid, as soon as the assumption check works. If it doesn't work, don't do the question. You do not need to do it whatsoever, because, well, that's the whole point. You're not expected to use the quadratic equation, so don't. That's it. Now you do have to be careful, though, if it is a strong acid, different rules altogether. So let's look at one more example, and then you should be able to get the last few examples on your own. So where it says predict the concentration of hydronium, pH, and pOH for a 2.0 moles per liter solution of methanoic acid, and they give you the Ka. Now what I'm going to do is just the assumption check up here. The assumption check. So the assumption check is we take the concentration of our acid and we divide by the Ka, and we see if this is greater than 1000. So our acid, 0.200 moles per liter. I don't need to put in moles per liter. The Ka is 1.8 times 10 to negative 4, right? And we're seeing if this is greater than 1000. And when we evaluate this, we get 1, 1, 1, 1, which of course is greater than 1000. So as soon as this assumption check works out, we can do this, because the assumption check works, we can go concentration of hydronium is the square root Ka times the acid. And we plug in our values, and we get our answer. Then of course from here, as soon as we get the concentration of hydronium, pH is equal to negative log and we get our value of 2.22. And remember, pOH is equal to 14.00 minus pH. We go 14.00 minus 2.22, and we get 11.78. So there's pOH, there's pH, and there is hydronium. So that is how we can use our assumption check to completely kind of shorten the amount of work that we need to do, but then also completely overhaul how we solve some of these questions. So really it comes down to just being careful what is the question asking, and of course solving it when it's done. So summarize right here, strong acids, we've done before, concentration of hydronium is equal to that of the acid. So weak acid, you need to do the assumption check. If the concentration of the acid over the ionization constant is less than 1000, we use the quadratic equation, and as I have right here, do not solve the question if that is the case. Just leave it blank. Say quadratic required, do not need to solve. If we have the assumption check greater than 1000, we use this and solve for pH and or pOH. So that leaves example 3, 4, and 5. I want you guys to try on your own. Now, once you get them done, please just log on to Google Classroom, check the answers to make sure that you get them right. And spoiler alert, because there's 3 conditions right here, so strong acid, assumption check less than 1000, assumption check greater than 1000, there are 3 examples left. So one of them is a strong acid, and you're going to do this. One of them is a quadratic, so you don't need to do it, and the other one is going to use this equation right here. So you should use one of these techniques for each of the 3 and just give them a go. So once you're done, check your answers with the answers online just to make sure, and come back tomorrow where we're going to look at base strength and the ionization constant. So I'll see you guys for the next one.